Okay, welcome back, everyone. Sorry for the technical issues. If we're not able to figure out the origin of this, then for the next class, I'll do it from my office on campus to hopefully at least rule out that as a internet connectivity as a home internet connectivity as the source of the problem. So to jump in where I believe we left off, we were talking about capticity, and this describes a single metal's single ligand's ability to interact with a metal in different ways and through a different number of atoms. The case study that we're looking at is metal benzyl species. A benzyl ligand can coordinate in two ways, either 8 to 1, where this is essentially just analogous to how a simple alkyl ligand like a methyl would coordinate. It's a 2-electron donor, -1, and an overall X type. Now, it can also coordinate through in an 8 to 3 fashion. One way that might be helpful to visualize this, might not, is to think of the metal as interacting both through the benzyl as an alkyl ligand and to the pi system as a neutral donor. And here, this I think is maybe helpful in seeing that this ligand would be described as LX type, thus a 4-electron donor, still -1 charge. And I think an interesting thing to note here is that the coordination number of a simple benzyl group is 1, and the coordination, A to 1 benzyl group is 1, A to 3 benzyl group is 2. And so the ability for a metal benzyl species, or analogously a metal al species, to toggle between A to 1 and A to 3 as a way of opening a coordination site on the metal to trigger reactivity. When we discussed Grignards and organolithiums, we talked about bridging interactions, so I won't rehash that discussion, but as a reminder, bridging interactions are denoted with the Greek letter mu, and the superscript defines the number of atoms that are bridged by said ligand. Let's consider a couple case studies here. So these are some common bridging ligands that you will encounter. Halides are one type. The example here is with bridging chloride ligands that in a mu2 fashion, bridging across 2 different metals. And so one way to think about this in terms of electron counting is to view the chloride ligand as being an X-type ligand on one metal and an L-type ligand through its non-bonding lone pairs to the other metal. So that's what is depicted here. Sorry, let me draw this in the way that you'd probably be likely to encounter it in an example. So so just drawing out the Lewis dot structure can help you think about to which it would be how it could interact both as a X-type ligand and a neutral donor. And in reality, quite often when there's one bridging interaction, there are actually 2 or more bridging interactions. So if we consider, let's say, 2 mu2 chlorides, then in reality it becomes irrelevant which one you define as having the X-type interaction, which one the L-type interaction in terms of your electron counting. Now, in reality, it's not accurate to say that it's actually X-type to one or L-type to the other, because typically these are symmetrical, and so the electron distribution is equivalent across both those bonds, and that can be read out through X-ray crystallography. But again, this part of this lecture is about bookkeeping, so this is how you can do your bookkeeping. Another type of bridging ligand that is common are bridging hydrides, and here it's kind of the same story, but with a slightly different twist. Now you don't have lone pairs on the hydride that are capable of serving as sigma donors. You actually have the sigma bonding orbital between the metal and one hydride serving as the sigma donor for another, or at least, again, that's one way to think about this. And Malcolm Green has suggested using half arrows for this type of interaction, but I'll draw this as a full arrow just to be consistent. And again, just like with the case of chlorides, often these bridging hydrides come come in pairs. So then which one you're defining as long as you draw the bonding picture as symmetric, it doesn't matter which is X type or which is L type. CO ligands are also commonly bridge metals, and here the situation is similar to what we're talking about, but now you just have one lone pair electron, one lone pair from the CO that's engaging in bridging between both of these metals. So let me kind of draw that. And so I think if you draw in this way, you might stand to reason that this lone pair can only give one, in terms of bookkeeping, one electron at a time to each of the metals. And so indeed, in terms of the electron counting, you can consider it as a 1 electron per metal donor. Here's just an example of how to translate structure into nomenclature in a molecular formula in a way that also depicts a structural element. So this is how the mu notation is used in that context. Another more complex scenario that is nevertheless encountered somewhat commonly are species that contain metal-metal multiple bonds. So one exercise that's important to be able to do is, from a given molecular formula, make a reasonable prediction about whether something is likely to have a metal-metal bond or a metal-metal multiple bond. And so there's actually a simple formula to do that. The formula is shown on this slide. The number of metal-metal bonds is equal to 18 times, again, this comes from the 18 electron rule, times the number of metals minus the total number of valence electrons divided by 2. So this, I think, in abstract is not super clear, but is actually pretty simple to follow when you work through an example. So let's consider this specific example of dicobalt octacarbonyl. We have 2 metals. The number of valence electrons is equal to, in this case, we have 8 CO ligands, each is a 2 electron donor. So 8 times 2 electrons, and we have 2 D9 metals, two cobalts. So N here is going to equal 34, and then we just plug and play. 18 times 2 minus 34, 36 minus 34 divided by 2 equals 1. We would expect there to be one metal-metal multiple bond. And indeed, one low energy form of this species is the one that I'll show here. And I sort of set us up for this. A lot of carbonyls can bridge, and so metal multiple bonds. It depends, but in general they're not particularly strong, or at least in this case it's not strong. So in solution, this is able to equilibrate between 2 forms, the form drawn, and then also a bridging carbonyl form. No change in oxidation state, still octacarbonyl. And if you're interested, you can find more details about some of the early studies on this complex in this reference from inorganic chemistry. Now, what we just discussed was, if you see a molecular formula, how can you make a prediction about metal-metal bonds, the number of metal-metal bonds, but an alternative situation that you'll encounter is just being shown a structure and then knowing how to electron count from that. So when you encounter a metal-metal bond, you should count it for one valence electron. So with that in mind, I'll leave it to you to compute the electron count for both of these forms of cobalt octacarbonyl as an exercise at home. Okay, so we're wrapping things up now. Let's just consider a couple special cases here, and these are cationic ligands. So we've talked about ligands that are neutral, they bring no charge. We've talked about anionic ligands, and there's a special case. You won't encounter this too often, most likely, but it's useful to know how to electron count in these situations where you have ligands that can actually be cationic. So the first one that we'll consider is NO. There are two flavors of NO ligands, linear NO and bent NO. Linear is more common. So if you're asked about an NO containing complex, just let's say from its molecular formula, then you should assume it's linear unless you're told otherwise. And if we just draw it out in its linear form, then that immediately defines that the NO bond has strong triple bond character, and that will help us with this exercise of going back to a closed shell species and then thinking about what that means in terms of electron counting. So let's go back to a closed shell species while keeping this NO triple bond intact. We're just drawing the Lewis structure here for clarity. And so that then shows that this is going to be a 2-electron donor, but actually have a +1 charge. And then the other situation is the bent form, where now the NO bond has double bond character. Again, let's go back to the closed shell form, the Lewis dot representation. Now we see that this would be anionic. So this too would be a 2-electron donor, like most ligands in the ionic electron counting model, but would have a -1 charge. Another interesting case study is tropylium. This is a 6-electron ligand that has +1 overall charge. And I think this is interesting because there's a nice isolobal series of related aromatic ligands. Namely CP, which we've seen, and just simple benzene or a simple arene. So all of these are 6-electron donors. As I said, these are isolobal. Tropylium is a +1 charge, benzene is obviously neutral, and CP is a -1 charge. Okay, let's now close things out by jumping over to the problems of the day, 2 through 4. These were meant to be interactive in the live session. I'll take a little bit of extra time here to walk through the solutions, and then we'll wrap things up. Let me quickly switch over to the actual worksheet for anyone who now doesn't have it handy. Bear with me. Okay, so questions 2 through 4. I'll read through all of them here, and then we'll jump back to the iPad. Number 2 is just 4 different organometallic complexes where we're asked to provide the coordination number, metal oxidation state, d-electron count, and overall electron count. 3 is a question that's open-ended, and we'll do this as a 2-minute essay response. when we get to it, where we're asked to consider how to characterize whether something should be a metal-metal putative interaction should be described as a bonding interaction or not, what the criteria are for that and what analytical techniques would be appropriate. And then question 4 is electron counting, but meant to foreshadow the next couple lectures, which will be on starting to build up the concepts of how to understand reactivity from structure. And so that asks us to consider this reaction below, where this CP titanium dichloride is treated with magnesium and THF, and in the presence of an alkyne, what is formed. Okay, let's jump back over to the iPad. For some electron counting. Make sure everybody is on the same page here. Okay, so what do we have here? Let's do our standard operating procedure. Let's first inventory our ligands. We have 2 L-type ligands from CO, and then we have this CP ligand, which is going to be -1. Remember, it's an L2X ligand, L2X. And then we have, this wasn't drawn this way on the problem on the problem of the day sheet, but I've drawn this here in the suggestive form. Remember, we have triphenyl aluminum, and this is going to form a Z-type interaction. So it's a 0 electron donor. So we have only one negative charged ligand, and we have to keep track that the overall complex is -1 here. So that means that we're iron 0. If we go to our periodic table and we ask what group is iron in, it's D8. And then if we have D8 electrons, and let's count it up, we have 2 CO ligands and then an L2X CP. So we have 10 2 electron donor ligands, so 10 electrons from the ligands, giving us overall an 18 electron complex. And we're also asked to consider the coordination number. And here, I think this is actually one of these borderline or debatable cases about whether we want to count the Z-type interaction as a coordination number or not. I don't think, you wouldn't maybe be asked about something like this on a test where it's not really clear definition. But so let's first assume it's not. Then you have the CP, which is 3 coordinate, and then each of the COs, which is monocoordinate. So it would be 5 coordinate if you do count the Z-type ligand as a coordination number. Then it would be 6 coordinate. Okay, now we have this PNP pincer iridium complex. Let's again apply our standard workflow. We have 3 L-type ligands, the both of the phosphines and the pyridine. So we have 3 L-type, and then an alkyl. And I have this drawn as a sulfur, but this is a silyl group. An alkyl and a silyl group. These are each X-type ligands. We have an overall +1 charge. So we have 2 negatively charged ligands. Overall charge is +1. So we can say this is going to be iridium +3 oxidation state. Iridium is in group 9, so that is going to make this D6. And then if we count the number of valence, the overall number of ligands from the overall number of electrons from the ligand, we have 10, giving us overall 16 electron species. The counter anion here is maybe just worth noting. This is BARF, which is a weakly coordinating anion with 3,5. bis CF3s in case you haven't seen this before. Okay, let's continue to move quickly. We'll actually just take on this manganese salin first. It's a little bit more straightforward. And this example you might recognize from, among others, the work of Eric Jacobson. So we have each of the phenoxides, which will be X type, so 2X, each of the amines, which will be L type. That means that the overall, and then I have there's a chloride here, I believe, that I didn't draw, which is, it should be 3X. So we have manganese plus 3. That's going to be D4 because manganese is a group 7 metal. There are 10 electrons coming from the ligand. And so overall, then we have a 14 electron complex. And then this last example, this has quite a bit going on. Let's first draw these bridging sulfide ligands in a more suggestive way to help with our bookkeeping. We'll do the bookkeeping here with respect to a single ruthenium. We have a ligand here that we haven't defined yet in this class, which is CP star. This is just a pentamethyl cyclopentadienyl, just a bulkier form of the classical CP. Okay, so now let's go through this exercise with respect to the left ruthenium. We have one of the sulfide ligands, which is going to be X type, the CP, which is going to be X type, the chloride, which is going to be X type, and then one L type interaction from the other bridging sulfide. So this is going to be ruthenium 3. D8. And then now we also, remember, have one electron from the ruthenium-ruthenium bond. Sorry, I drew this CP quickly as X type, but it's of course L2X. And then if we count the number of ligands, it's going to be 12. And overall, we're going to get to the an 18 electron complex. And this is a catalyst that's used in propargylic substitution by Hedai, in case anybody is interested in reading more about this. I'll provide a reference too for this example in case anyone's curious about that. Okay, problem of the day number 3 is our, as we said, our more open-ended problem. So this asks us to consider this complex and think about analytically how we would try to characterize whether there's a metal-metal bonding interaction. So if you're taking the class now for credit, I'd ask you to take 2 minutes, pause the recording, and do a 2-minute essay and send that to Van about how you would approach this. And let's say you want to use 13C NMR. I would not recommend that in this case, but let's say that's your approach. Then don't just say 13C NMR. Try to explain what you would expect to see that would allow you to characterize whether there's a bonding interaction or not. Okay, so let's go through some possibilities. No, not necessarily any right or wrong answers here. So I think, you know, one possibility that probably immediately comes to mind is to try to get an X-ray structure. And then what you'd be looking at is whether the sum of the van der Waal radii, or the bonding, the distance between the two elements is less than the sum of their van der Waal radii. Another technique you could use is NMR. Here, probably the easiest thing to do would be or the most direct way to interrogate this would be to use aluminum NMR, which I believe is 27 aluminum NMR, and compare the chemical shift of aluminum in the presence and absence of nickel. And there are others. So I would say, just off the top of my head, you know, you could think about like coordinating a CO ligand. You'd have to make sure that this thing remains intact, and then seeing how the CO stretching frequency changes as a function of whether the aluminum is there or not. So this problem is an example from our chemist of the day, who is Connie Liu, and here's the reference. From University of Minnesota. They call themselves U of M, but I'm a University of Michigan graduate, so I can't stand to write it as UM, so that's why I write it as UMN here. And Connie, just in terms of her background, she was an undergraduate at MIT, did her PhD with Jonas Peters at Caltech, and then a postdoc at the Max Planck Institute for Bioinorganic Chemistry with Carl Wiechert. She's been at Minnesota since I think 2009. So, you know, if we count pandemic time as not really existing, then she's just within our 10-year cutoff, and she's established a really vibrant program in heterobimetallic complexes and their reactivity. I remember when I was a postdoc and I saw her give a talk at Caltech, she mentioned that one of the inspirations for the genesis of this program was thinking about the dirodium complexes, particularly rhodium ESP, that Justin Dubois has used for nitrogen transfer, and thinking about how to develop syntheses, modular syntheses, to put any metal that one might want in these sort of bimetallic scaffolds, which I think is really interesting. And so she had said she saw a talk by Justin as a graduate student and kept that idea in her mind. So I tell that story just to encourage you all to it's never too early to start thinking about what would be interesting to work on in your independent career. Okay, problem of the day number 3, sorry, problem of the day number 4. So if we look at the reduction potentials of titanium here, this is well. Let's go ahead and do our bookkeeping first. So we have 2 CPs on titanium, 2 chlorides. So we have 4 anionic charges to account for. So this is going to be titanium 4, which is then going to be D0. And then if we count for the number of electrons from the ligands, we have 1, 2, 3, 4, 5, 6, 7, 8, and 8 times 2 equals 16. So it's overall a 16 electron complex. Now it's if we look at the reduction potentials of titanium 4 and magnesium 0, then we would be able to predict what is going to happen in this reaction, which is that initially titanium is going to get reduced, and then we have this alkyne present. So presumably something is going to happen with the alkyne. So let's first draw. So let's first sort of consider what the implications of this would be as titanium gets reduced. So if we reduce down to titanium 3+, then the bonding interaction between titanium and chloride would become weaker, and as we reduce down further, and this would all fall out of the reduction potential, the redox potentials, then we could get down to titanium 2+, and the second chloride bonding interaction would become less favorable. Now titanium 2+ is and we've also in doing this reduction have kind of created vacant coordination sites that are capable of binding the so let's say we have an open coordination site now. The alkyne is able to sit in this coordination site. And now because titanium 2 is relatively electron rich, this can actually react, or this interaction, we'll talk later about how one would predict this, but this actually is best depicted as a metallocyclopropene. So that's going to be the answer to A. So we have titanium, CP, CP, this metallocyclopropene. Titanium 2+, excuse me. So as drawn like this, where we actually have a bonding to an alkenyl fragment, this will be, each of these will be X type. So we have X here, X here. So this will be still, we reduced, but then we coordinated the alkene, and we did what we'll learn later is called an oxidative cyclometallation to get back to titanium 4+, D0, and then 8 ligands with 2 electrons each, 16 electron complex. And now it turns out that this reaction, or this process, is actually reversible. So that both the coordination and the oxidative cyclometallation are reversible in this case. So let me draw this back out as a putative intermediate. So this would be the intermediate structure. I'll draw this. Try to draw this clearly. With B, which would just be this now being fully dissociated. So I think hopefully this example will set the stage for the next couple classes. So here now we have titanium 2+, D2, and 14 electrons. Sorry. $12 electrons coming from the ligands, giving an overall 14 electron complex. And one of the keys that we'll discuss in more detail is that for these oxidative cyclometallizations to take place, you do need d orbitals on, you need filled d orbitals on the metal. So hence this D2 is actually consequential in this case. So that's it in terms of the content. Again, sorry about the connectivity issues. I'll close just by quickly returning to our problem of the day, which was our problem of the day worksheet, and draw your attention to the quote of the day, which is that all things in the night are larger, more fearful than by day, and are smaller when clearly discerned. And this was quoted in an obituary written of Fisher after his passing, and sort of a reflection on his life. And it was in reference to the rivalry that was sparked between Fisher and Wilkinson after their back-to-back publications regarding the structure of ferrocene and all the resulting work on metallocene. And so this was a quote that reflected his ability to stay calm and reason through new areas of research while working in a very competitive area. So on that note, I'll close things out and see you on Tuesday. Have a great weekend, everyone.